Okay, so the next thing is we're interested in the distribution on the H0 and on the H1. So we will take a look at the detection performance uh, can be found by noting that on the H0, let's take a look. On the H0, we are actually taking what? The test statistic is a summation of the square. But the summation of the square is just the summation of the square of a Gaussian random variable W, right here, W. So as a result, when you take the sigma square as the denominator, you get chi-square. Remember in chapter 2, we introduced a lot of distributions. We have chi-square distribution, right? We have Rayleigh distribution, we have Rayleigh distribution, and then this is the chi-square distribution. So uh, the reason is that when you have W, you have to divide it by you divide it by sigma square, then that W will be W divided by sigma will be standard Gaussian, and then the sum of the square of the standard Gaussian will be chi-square. Then how many variables do you have? You have n variables. As a result, it has degree n. You see that subscript degree n, right? And then the same thing applies for H1. You are summing, you are making a summation of the square of Gaussian random variable with the the variance to be something like this, and then of course you divide its variance at the denominator, and then you get standard Gaussian. You sum it up, you get chi-square. Okay, so that's the distribution on the H0. That's the distribution on the H1. So the statistic in the sum of the square of NIID Gaussian random variable. So to find PF and PD, we recall the right tail probability for chi-square. That is also in chapter 2. So the right tail probability of a chi-square is Q. We will have a notation for Q sub chi-square V, then X equal to X to the infinity P of T dt. Then what we do is we take Q chi-square of X equal to the standard Q function. Notice that the Q function is the without subscript. Q function without subscript is a standard Q function, and Q function with subscript chi-square is a right tail for chi-square. So that's different. Okay, this is different, and we are more familiar with Q function actually. If you, as we say, if you look at Python, MATLAB, or whatever mathematical tool you have, most likely it has built-in Q function. So you can, for example, Q of 1, Q of 2, you can just type Q of something, then it gives you the value. But Q sub chi-square is not that common. This is more like a special case. So we will express that Q sub chi-square in the form of the standard Q function, because the standard Q function is more formally more available. So if it's V equal to 1, uh, if that V is equal to 1, then it's 2 times Q of square root of X. So this is just a functional form correspondence. Okay, even without any physical interpretation, you can think of this as just a mathematical correspondence. So Q of this is 2Q of something. And then Q of this for V is larger than 1 and arced. Then it's 2Q of this thing plus exponent of this over square root of pi, then summation of this k1 to v minus 1 over 2 and k minus 1 factorial 2x k minus 1 over 2 over 2k minus 1 factorial. So this is more like a more complicated form. And then if v is even, then it looks like this. You have exponent parenthesis minus 1/2 x summation v over 2 minus 1 x over 2 and so on and so forth. So from 5.1, uh, we will have PFA equal to probability of T of x larger than gamma prime condition on H0. How come? Think about this. If T of x is larger than gamma prime, then we will decide H1, right? But condition on H0, we decide H1. That is exactly the definition of probability of false alarm. So that is the false alarm probability. And then condition on H0, of course, we can divide it by sigma square. Why? Because we want to fit into this form. We want to fit it into the standard chi-square. As a result, we divide it by sigma square. So T of x sigma square, gamma prime sigma square. Then, of course, for this thing to be chi-square distributed, then we can use the right tail distribution right here. That's the right tail of a Gaussian. From where? From gamma prime over sigma square. So that's sort of like a chi-square distribution, and from some point it goes on this small area. That's the right tail, and it will be expressed by q sub chi-square n of gamma prime over sigma square. And then PD will be probability of what? Condition on H1, and you divide, and then your decision is H1. And then what that means is you want to divide this by, you want to make it equal to this thing, right? Because we want to make it to chi-square. So T of x divided by this, and gamma prime divided by this, and it's a right tail. From where? From here. From gamma prime over here. So that's PFA as a function of gamma prime, PD as a function of gamma prime. Of course, they are sort of being divided by sigma square and sigma s square. So that's the thing. So uh, so from here, and from here, we can set a gamma prime and calculate the PFA, and then plot a PD versus sigma s over sigma square, right? If you think of this, gamma prime, when it's set, for example, you set a, let's say 1 in here, then PFA is known already. So once PFA is known, then you have this PD as a function of sigma s and sigma square. As a result, you will be able to plot PD versus here for a given PFA. So for example, PFA is 10 to the minus 1, and you get this plot. PFA is equal to this, you get a plot that is lower. So you get PD to be lower. That the whole thing seems to be reasonable, right? When you have better PFA, you sacrifice a little bit on PD. It's sort of a trade-off. Okay, so it should be noted that the threshold can be found from 5.2. 5.2. The reason is that when you, for example, you like this to be 10 to the minus 2, you're given the sigma square, then you just do the inverse function of q chi square, and then you get gamma prime. Okay, kind of an inverse function for q. So also the detection performance increases monotonically with SNR. That is also reasonable. And SNR is defined by sigma s square over sigma square. To see this, we assume that for given PFA, the argument in 5.2 is like this. We just change the variable again. Then you see, you do some reformulations. You get PD equal to something like this. Then, of course, then you get PD as a function of sigma s over sigma square. Then you get this plot. Okay. So, we can generalize the energy detector to signals with arbitrary covariance matrices. So, to this, we assume S is a zero mean Gaussian random process with matrix C of S. Then, as before, Wn is white Gaussian noise with this. So we have X distributed now with noise only here, or we have a noise that contributes to this term, and then signal contributes to here, but it's no longer identity. It has a covariance structure. All right. So the NP detector will decide H1 if this likelihood ratio is something like this, and then this is what? This is again, let me just maybe skip some of the details just to explain the rationale. And I think if you are interested, try to do some derivation. This is a probability density function on the H1. This is the probability density function on the H0. So this is likelihood ratio, H conditional H1 over P of X conditional H0. And you will decide H1 if this is larger than gamma. Okay, if this is larger than gamma, you decide H1. That's the likelihood ratio detector, right? And again, we do the same thing. Take log, return only the data dependent terms. Okay, we will return only the data dependent terms. Then we get something like this, because this is not data dependent. This is not data dependent. They all disappear. And the only thing that remains is this term and this term. Of course, there is the exponent, so they will be minus with respect to each other, and then do some simplifications, you get this. And then we do reformulations, we get something like that. You basically you take 2 to here, you take sigma square to the right hand side, and you get something like this. And then of course you have to reverse the turns, reverse this turn to from reverse this turn to the back, so that you get this minus 10 to plus 10. So we get t of x equal to this larger than that. Notice that when we are doing the simplifications, we go all the way down here. Mathematically, we are doing the same thing. All right, we are doing, just don't get confused. We are still making decision for h1 under here, and now we are making decision on h1 under here. All right. And then there's matrix inversion lemma for this. This is an identity，这是一个矩阵的恒等式，但是推导是当然是蛮复杂的。So we're not going to do the derivation, but we use this lemma and let a equal to this term, something here, a equal to something here, and this c equal to cs, and things like that. You do some equivalent correspondence, and then we will get this term equal to this term, so that you take this term into here and do some simplifications, so you get t of x equal to xt, square bracket x, and then in the middle, you know that you notice here there is xt, and there is x, xt, x, and then in the middle it's this one goes in, and then in the middle you have this thing that seems to be simpler than before. So we will let s hat equal to this term. Uh, so this term is can be simplified. In fact, what we are trying to do is we're trying to uh, rename this whole thing as S hat. And we rename this whole thing as S hat. And we do some simplifications. We get CS plus sigma square I minus 1 to the minus 1x. So we will decide H1 if this, right? If this. But then this term has been denoted by S hat. As a result, it becomes ST multiplied by S hat. So we'll decide this if xt multiplied by S hat is larger than gamma double prime. The reason for gamma double prime is that we just have a new threshold. Okay, new threshold. Think about this. We have some variables that is in fact it's not variable, it's constants. Some constants are put at the right hand side. So we will just make the right hand side to be a simple notation, and then we call it gamma prime, gamma double prime. All right, so we have xt x hat uh, equal to summation of xn, because if we write it out, x is something like this, right? You take the transpose, then you get a row, for T transpose. No, you get a S hat, that is S hat. So you have a row, you have a column, then first element with the first element, second element with the second element. So you write it all out, you get something like this. So that's kind of our uh, kind of what this is our so-called test statistic. Then again S hat has to be clarified. It's something like this. So the NP detector correlates the received data with the estimate of the signal. Therefore, uh, let me clarify a little bit. This X is a received signal. Then we multiply this S with this term. It's kind of a operation on received data X. And then we come up with this S. And if you see the dimension, you will find X to be a column vector. S hat to be a column vector also. As a result, we will see it's a perspective. We use the perspective of an estimator. We will say that we estimate the signal S with this operator, and it's a linear operator because it has only multiplication of the matrices, so it's an operator, and we operate on data and we get an S hat. Then we will call it an estimate of the signal. We call this an estimate. So as a result, let's recall and come back to see this again. This is in fact a correlation, right? Mathematically, we can think of this to be a correlation between received data and S hat. However, S hat is an estimate of the signal. So as a result, we can call this an estimated correlator. We estimate the signal from the data, and then we correlate the data with the signal. So it's an estimated correlator. But the point is, this is still uh, a, a likelihood ratio detector. Okay, it's just a way that in which we interpret it as an estimated correlator, but it does not mean that estimated correlator is always the best. No, no, that's not what we mean. What we are actually saying is this is an estimator. It comes from likelihood ratio. That log and then of course simplification of likelihood ratio. That's what we say. And it happens to has this interpretation of estimated correlator. Okay, so note that the test statistic is a quadratic form in data and that will not be a Gaussian random variable. Okay, we claim that S is actually a Wiener filter estimated for the signal. It should be emphasized that although S is a random process, interpretation of S hat is an estimate of the given realization of the signal. Okay, so again, S is a random process, but it's an estimated version. And then the interpretation is the realization. Remember that in the beginning of our class, I like to emphasize some of the basic concepts of probability. When we say something is a random variable, it's a random variable. And I want you to distinguish between the random variable and the realization. Okay, so now here is the estimate of the realization of the signal because S is by itself a random process. There's not supposed to be an estimate for the signal because it's just a random process. It realizes itself each time and each realization will be different, right? So, of course, then this thing is called Wiener filter because it's first invented by a person named Wiener. It doesn't matter. It doesn't matter. It's just a name. This thing is just a name. Okay, and then uh, theta is a unknown random variable whose realization is to be estimated based on the data vector x, and theta and x hat are jointly Gaussian with zero mean, then the MMSE estimator is something like this. Is something like this. And then of course the C, this is the cross correlation, right? Cross correlation. C theta x is expected theta xt, and cxx is expect cxt. So this is the MMSE estimator for theta hat. And note that the MMSE, there are more complicated arguments behind this, but we're not elaborating too much on this because it has deeper and more complicated derivations. But we just think of this as MMSE estimator. In fact, what we are doing is when x theta and x are jointly Gaussian, then this is the minimum mean square error estimator for theta hat, given the realization of x. So this can be proven to be MMSE, but no proof is provided here. Note that the MMSE estimator is linear due to the joint Gaussian assumption. So if we think of theta equal to s, x, notice that this s is a random variable because it's a random process and been taken samples from 0 to n minus 1. Recall this. And then x is s plus n, and s and w are uncorrelated. The MMSE estimator coming from here, we can get this, right? This is MMSE estimator, and then the MMSE estimator is to here. As a result, we get something like this, and we get this. So what that means is estimator, correlator, estimation is also a MMSE estimate. The signal power is also MMSE estimate. So we have X comes in, and then it goes through Wiener filter. In fact, it's just a linear operation by this. Okay, uh, if you think simple, it will be just a linear operation of the matrix. Okay, and then it goes as head and then multiply together and sum it together, which is the correlation. This is the correlation, and this is the Wiener filter, and you get T of X, and you compare it with H0, H1, and then you get this Gaussian noise. You get this Gaussian. No, you get this detection. You get this detection. Okay, and then if the signal is wide, then CS is sigma SI. The signal estimator is something like this. Then it goes to this. Okay, it goes to this. So this is kind of zero memory filter because Sn is only related to Xn. Okay, and by a fixed scale factor. This. Okay. And then in this case, the detector simplifies by incorporating the non-scale factor into the threshold. Let's we will decide H1 if this is larger than this, and then you put this at the right hand side, you get something like this. This is what? This is like example 5.1, right? It goes back to 5.1 if C is equal to this, then it's simple. Then if it's correlated signal, I will go quickly. If it's a correlated signal, then yeah, you will we will have to assume CS equal to sigma S squared, and like you have a law at the correlation part, which is not a Y signal anymore. It's a correlation coefficient, and then the test statistic is something like this, right? And then instead of expressing the test statistic in terms of X, it's better to let Y be dx where V is equal to this. Then since Vt is equal to V minus 1, we have something like this. And then you have V CSV equal to lambda S lambda. This is like what? Eigen decomposition, right? And this V is like eigenvector. And then this is eigenvalues. So the test statistic becomes something like this, and then you get YTA, where A is this thing. So we have test statistic equal to something like this. Then the data are first linearly transformed from X to Y, after which a weighted energy detector is applied. This is like Y0 plus Y1 squared, but weighted by this term and this term. Okay, so but if low is 0, then the signal is Y. We have just this term. That will go back to the the Y Gaussian signal case, right? Okay, so we will take a break and then come back later.